Hi, this is Dan from Mechanical PE Exam Prep. If you were watching the video of the controls problem from 101 Solve Mechanical Engineering Problems, we got to a point where we had this differential equation to solve, and I didn't want to bog that video down and make it even longer with heavy math, so I decided to peel it off into a separate video. Now, you probably won't have to solve a differential equation on the PE exam, but if you found that solution unsatisfying and you want to know how we got from that complex equation to the general solution that I basically skipped straight to, this video will take you through that math. So this was the equation we had. There's different kinds of differential equations. So, I mean, I had to open up the books because I don't remember how to identify the different types, but this one can be solved with what's called an integration factor. But the first realization is that it fits a particular form. So we'll talk about what that form is. The first thing you can do is get t prime of t by itself. I'm going to divide by 11.79t plus 600 in all three terms. And what that'll give us will be t prime of t plus 41.79 over 11.79t plus 600 times t of t equals 19,332 over 11.79t plus 600. And now I will remind you about something that you probably don't remember unless you're taking differential equations right now. This fits a particular form that is very useful, which is y prime plus py equals q, where p and q are functions of x. So I'm switching variables a little bit here. You can imagine that our capital T for temperature is y and our little t is x. So if p is a function of x and q is a function of x, then this is basically our y prime. You can think of this as y prime. This whole thing is basically our p, this is y, and this whole thing is q. And the reason this fits the form is because p and q are only going to be functions of x, or in this case, p and q are functions of t, but we're gonna switch variables to make it a little more mathy, and it's getting less and less descriptive about the actual physical tank problem that it came from, but that's okay. We can put it back into temperature and time at the end. I'm gonna work in y and x since it's just more common in math problems. So if you have something that fits this form, I'm gonna do this kind of generally first, and then we'll do it specifically as it relates to this problem. If you have something that fits this form, y prime plus py equals q, then you can define what's called an integration factor. And we'll call that mu. Sometimes they write mu of x, but I'll just call it mu. And this is defined as e raised to the integral of p with respect to x. So basically it's whatever this middle term is being multiplied by, whatever y is being multiplied by, it should only be a function of x. And if you take e to the integral p of p dx, then that gives you your integration factor. And once you do that, you multiply both sides of the equation by mu. So working from here, you end up with mu times y prime plus mu times p times y equals mu times q. And now you can integrate both sides. So on the left side, we take the integral of mu y prime plus mu py with respect to x, and on the right side we take the integral of mu q with respect to x. And this is where something interesting happens. What's the derivative of mu times y? And I promise you this is going somewhere. Well, mu is a function of x only, and y is a function of x. So in order to take the derivative, we need to use the product rule. So we can do mu times the derivative of y, so mu y prime, plus mu prime times y. But here's another thing. What's the derivative of mu, right? We have a mu prime in here. Well, we know mu is e integral p dx. So the derivative of mu with respect to x is going to be, the derivative of any exponential is itself. So e integral p dx times the derivative of whatever e is being raised to. Well, the derivative of the integral of p dx is just p. So that's times p. So if and now what is, I can make a substitution back, e integral p dx is mu, right? So substituting that back in, the derivative of mu with respect to x is mu times p. And I know this seems like a little clever here, but that's the whole design of using this integration factor. That's why this whole thing works out the way it does. So, you know, it's e raised to the integral of p for a reason. And now I'm going to go and substitute that back in. This is mu prime, right? So for mu prime, I'll write mu p instead. So now this thing equals mu y prime plus mu p y. Now, why is that so interesting? Well, if the derivative of mu times y is this whole thing, it just so happens that when we integrated both sides, we have that whole thing on the left being integrated. So its integral must be my. If the derivative of my is this, then the integral of this is mu y. So mu y equals the integral of mu q dx, substituting mu y for the integral of this whole expression with respect to x. And now we can hopefully find the integral of whatever mu times q works out to be with respect to x, and then at the very end we can divide by mu on both sides and get y by itself, and that should be the general solution for our differential equation. Okay, so that's a little abstract. Now let's work through our actual equation and find the general solution. Okay, so for us, we started out with something that looked like it had the form of y prime times ax plus b plus y times c equals d. And I'm going to use these constants a, b, c, d so that we don't have to write the numbers over and over and over again. So a will be 11.8, b will be 600, c will be 41.8, and d will be 19,332. Okay, and then we rearranged this because we wanted to get y prime by itself. So we divided by ax plus b on both sides of the equation, and we ended up with y prime plus c over ax plus b times y equals d over ax plus b. And we'll call this equation 1 because we may have to refer to it after. And just to relate this to what we wrote above, this is going to be our p, and this is going to be our q. Okay, so the next thing we have to do is define mu, our integration factor. So mu of x equals e raised to the integral of p of x, which for us is c over ax plus b with respect to x. Well, let's just deal with that exponent by itself for a moment and get that integrated. So what is the integral, I'm jumping over here for a minute, what is the integral of c over ax plus b with respect to x? Well, c is a constant, so that just passes through. And whenever you have the integral of 1 over some function of x, it's the natural log of that function. So this is ln ax plus b. And then if we were, the way I remember it is by chain rule, if we were taking the derivative of some function of x, we'd have to multiply by a after, but since we're integrating, we have to divide by a. So I'll multiply out here by 1 over a. It's kind of an afterthought, but you have to include that as well. And then just simplifying, this equals c over a times ln ax plus b. And that's not mu, that's just what e is being raised to in mu. So if we bring that back to finding mu, it's e to the c over a ln ax plus b. And now you may remember a property of logs where you can take the coefficient of the natural log and make it the exponent on the thing that you're taking the log of. So let's apply that right here and make c over a the exponent on ax plus b. So what we'll end up with is e to the ln ax plus b, where ax plus b is being raised to the c over a. And now we get a very nice simplification. E to the ln cancels out, and you end up with ax plus b raised to the c over a, which is quite a bit simpler than we would have otherwise had. So that's our integration factor. And now, following the procedure we talked about before, we're going to take that mu and multiply both sides of the original equation, equation 1 that we marked up here, by mu. Okay, so we're going to get mu on the first term is ax plus b raised to the c over a times y prime plus ax plus b raised to the c over a times c over ax plus b times y equals ax plus b to c over a times d over ax plus b. Now let's just remind ourselves what each of these are so that it's really clear. This is mu times y prime plus mu times p times y equals mu times q. So that's just fitting with the method that we discussed earlier. So now we're going to simplify, and then we're going to integrate both sides. Now we already know that when we integrate the left side, we're going to end up with mu times y on the left. So rather than do all this algebra, I'm going to take advantage of the fact that we know where this thing is going, and I'll just write mu times y on the left. And then on the right, we do actually have to simplify mu times q, and then we're going to take the integral of it with respect to x. So multiplying these two together, we have this ax plus b in the denominator can be expressed as ax plus b raised to the negative 1. So the d is a constant that comes out. So it's d times the quantity ax plus b raised to the c over a minus 1. And we're taking the integral of that expression with respect to x. Okay, so let's take a shot at that integration. I'm going to pass the d through and write integral ax plus b raised to the c over a minus 1 with respect to x. And now we want to increase the exponent by 1. So that's going to be d times quantity ax plus b raised to the c over a, since we've increased the exponent by 1. And then we have to divide by the increased exponent, which is c over a. And then by chain rule, we have to multiply by 1 over a, which is like dividing by a for the inside function. And then these a's cancel, so we end up with, oh, I should also include, as soon as you integrate is when you have to start including an arbitrary constant. So if we simplify, we'll get d over c times quantity ax plus b raised to the c over a plus k. Now that whole thing is equal to mu times y. So let's now divide by mu on both sides. On the right side, it's just going to cancel, and you'd be left with y. But on this side, I'm going to actually divide each term by mu and show all that work. So d over c times quantity ax plus b raised to the c over a divided by ax plus b raised to the c over a, which is mu, plus some arbitrary constant k divided by ax plus b to the c over a. That's what y equals, and we can cancel these terms. So finally, y equals d over c plus k over ax plus b raised to the c over a. That's the general solution. Now, if you have an initial condition, which we did in the actual problem, you can apply that and get the particular solution, which basically means you're finding k. And of course, if you want to put this back into more tangible terms, since it describes a real physical situation, it's not just a math problem. Y is the temperature in terms of time t, which equals d over c, 19,332, divided by 41.8 plus arbitrary constant k over 11.8 t plus 600 raised to the c over a, which is 41.8 over 11.8. And that's the general solution to the differential equation. So hopefully that, I mean, I don't know if that will so much help with solving the example that we did, because realistically, finding an integration factor, it just really has no place for the PE test, even though there's really no other way to solve a transient problem. But in either case, it should scratch a math itch that you may have when you encounter an engineering problem like this. So any questions or comments, please leave them below this video or send me an email. Otherwise, I'll see you in the next video.